So as the name implies, photoelectric sensor converts radiation signal, light signals, or any other electromagnetic radiation in the form of visual radiation or in the other region, infrared radiation as well as ultraviolet as well as X-ray, towards electrical signal. The effect is called as photoelectric effect. So this effect is the primary element. The photoelectric device is the primary element that constitutes photoelectric sensor. They usually have quick response. The structure is simple. There's that material, which by itself it has this inherent photoelectricity effect, so that can convert any radiation, incoming radiation, into flow of current, flow of electrons or current. And it has the ability, of course, to detect signal without contact. One type of photoelectric sensor is photoresistor, or we call it popularly also as LDR, light dependent resistor. Usually one of the most famous LDR is cadmium sulfide cell. This is a resistor whose resistance decreases with increasing incident light intensity. It can also be referred to as a photoconductor. A photoresistor is made of high resistance semiconductor. So when cadmium sulfide itself is a semiconductor, so when there is high frequency light, containing enough energy, the photon will be absorbed by the semiconductor. Excuse me. And this will give the bound electrons in the valence band enough energy to jump into the conduction band. From valence band into conduction band, resulting in free electrons, and including the hole that is made in the valence band. So then you can see it either as from the electron point of view, where the electron flows from one atom to another, or from the hole. The hole also flows in the opposite direction, and therefore electricity is being conducted, lowering the resistance. Photoresistor, known as a light tube, is an optoelectronic device made of semiconductor materials. No polarity, just resistance. So without the illumination, the dark resistance is usually very high. So the current is very small. The dark, we call it dark current. So the dark current, when you purchase a photoresistor, then this is one of the specifications mentioned usually in the data sheet. The dark current of that photoresistor. The dark current is the current flows through that photoresistor when there is no light at all. When it is exposed to light with a certain range of wavelength, yes, it is not sensitive towards all wavelength, but usually in visual wavelength, then the resistance will decrease. The bright current will also increase. So the greater the dark resistance, the smaller the light resistance, the bright resistance, then it means the higher the sensitivity of that photoresistor. The greater, it means when the dark resistance is high, the dark current will be very small, so it doesn't conduct electricity when there is no light. When the light resistance is small, when there is light, when the bright resistance is small, then immediately when there is light, it can conduct electricity easily. So this shows the structure of a photoresistor. It consists of a semiconductor connected with two electrodes, metal electrodes, and usually at the other side, it has this glass substrate where light can go through, can pass through, and affect the semiconductor. And this is how it looked like, usually with a meandering structure of a photoresistor. This that shows the electrode. So the wiring diagram is like this. It's a resistor with symbol of arrow coming into that resistor, yeah, photoresistor. So some important parameters: the dark resistance, the resistance value without the effect of light, when light is not there at all. The corresponding current is called dark current or dark electricity. The bright resistance is the resistance value within the effect of the light. The corresponding current is called as the bright electricity or bright current. Then photocurrents is the difference between the dark resistance and the bright resistance. So when you see the datasheet of a photoresistor, you can read or you can see the volt ampere characteristic. How under the certain illumination, the relationship of the current and versus resistance will change, and this is called as the volt ampere characteristics. And there is illumination characteristics, the relationship between the photocurrent and the illumination intensity. Most photoresistors' illumination characteristics are nonlinear. Then spectrum characteristics. This will be the relationship between the relative photosensitivity of the photoresistor and the incidence wavelength is defined as the spectrum characteristics of the photoresistor or spectrum response. Then we have the temperature characteristic. So in spectrum characteristic, we will know at which wavelength the photoresistor is sensitive to. Okay. And sometimes even the same material will have different photosensitivity due to the change of the wavelength. Temperature characteristics, this will affect the spectral response as well as the sensitivity of the photoresistor. Yeah, the dark resistance is also greatly affected by the temperature. So because you see that in semiconductor, the valence electron can be excited into the conduction band. Either actually we want it only to be excited by light radiation. But of course, when temperature increases, then the heat will also give some thermal energy and may excite the electrons to go to the conduction band. That is why the dark resistance will also be affected by the temperature. Okay, the next type of photoelectric sensor is what we call as photodiode in transistor, I believe. Maybe you should have used it in one or other ways, until now in your electronics device or other lab practice. So a photodiode is a type of photodetector capable of converting light into either current or voltage depending upon the mode of operation. In photodiode, the electron, the current is generated from the junction, from the PN junction, at the PN junction. Without the light, without illumination, the reverse resistance is very large, and the counter current is very small. When PN junction is exposed, then this will induce photoelectron and photoinduced hole or cavities near the PN junction. Photocurrent will form, the current will flow. In other words, without the illumination, the diode is the cut-off state, and under the light, it is in the conduct state. And the symbol is usually a diode with having two arrows pointing towards it, symbolizing the light. So photodiodes, similar to regular semiconductor, they may be either exposed to detect vacuum, UV, ultraviolet, or X-ray, or packaged with a window or inside optical fiber to allow light to reach the sensitive part of the device. Yeah. In phototransistor, on the other hand, it has not only single PN junction, but it has two PN junctions. When the collecting electrode connected to a higher electrical potential than the emitting electrode, it will leave the base electrode unconnected, Collecting electrode will have here inverse bias potential. Here we'll have inverse bias potential. When light irradiates to the collecting electrode, the electron-hole pair will appear. The photo-induced scattered electron will be pulled to the collecting electrode, and hole will be in the base electron. Here, then increasing the electrical potential between base and the emitter. Between base and emitter. Therefore, the electrons will flow to the collecting electrode from the output current. The current flow in the opposite direction of the electron flow, of course. So this is the circuit according to the Darlington photosensitive transistor. So the circuit is being driven by illumination, by light here. Some basic parameters which we need to take into account for phototransistor and photodiode, basically similar to photoresistor. Some of them are similar, like the spectrum characteristics. This is at which wavelength that photodiode or phototransistors are sensitive to. For silicon, the peak wavelength is in about 0.9 micrometer, so in near infrared region. Germanium is middle infrared region at 1.5 micrometer. Then there is fault characteristic. Under the illumination, the counter current will increase if the illumination intensity increases. So this is so when the different illumination intensities, the fault ampere characteristic curves are almost parallel. That unless it reaches saturated, the output will never be influenced by the value of the different voltage. So this is similar like in the normal transistor characteristic. We have also temperature characteristics, where usually the temperature is similar to photodiode as well as photoresistor may induce leakage current, dark current. And temperature changes light current very little, but change the dark current greatly. And therefore, measurement with electronic circuit should be carried out on the dark current temperature compensation. It is always necessary to have temperature compensation for dark current. Yeah, since we need to detect light in many different applications, that's why PN photodiodes, phototransistor are being used in many devices. It's a consumer device, compact displayer, smoke detector, receiver for your remote control, and other application of light detection, pulse oximeter, also for computed tomography, and with scintillator, coupled with scintillator to detect the incoming X-ray radiation. Okay, next type of photoelectric sensor is the photovoltaic sensor. So in this case, then it will generate immediately voltage. The incoming radiation will generate voltage or electromotive force upon exposure to electromagnetic radiation. Okay. In photoelectric effect, there is the difference with photoelectricity and photovoltaic. In photoelectric effect, the electrons are ejected from the material surface when it is exposed to radiation having enough energy. Enough h nu. H is the Planck constant times the frequency. Nu is frequency. If this has larger energy than the energy gap between the valence band and the conduction band in that material, the electron will jump to the conduction band and can travel as a current. In photovoltaic, however, it is different. The electron is generated from different bands, from the valence to conduction band within the material, resulting in the build-up of a voltage between the two electrodes. So this is a photo-induced voltaic effect. You have p-n junction as well. Okay, and this n-type silicon. This is the p-n junction. This is p electrode, and well, this is the boron to have a p dope silicon. So positively doped silicon. Okay, when So this is the symbol, because it creates an electromotive force of like a voltage source when current flows. Sorry, when radiation is exposed to that device. The characteristic of photovoltaic device, similarly, it has also spectrum characteristics. It is sensitive towards certain band of wavelength. Also, in then illumination. For example, here silicon photovoltaic is between 0.4 to 1.2 micrometer. Selenium is between 0.38 to 0.75 micrometer. It has also illumination characteristics. At different illumination, how much photocurrent or photoelectromotive force is being generated. Temperature characteristic as well, because of it can create temperature drift of the photovoltaic. Then another quite different type of photoelectric sensor is fiber optic sensor. We can use, usually it's fiber optic sensor. Fiber optic is used to carry light radiation. It can be used as either as a sensing element, as intrinsic sensor, or as a means of relaying signal from a remote sensor to the electronics, in which case it is called as an extrinsic sensor. Why? How can it be used as intrinsic sensor? Because how the light propagate inside the fiber optics will depends on the strain, the bending angle, the strain along that fiber optics, as well as the temperature and pressure. So when the fiber optics is being exposed to this stimuli, it may create, it can modulate how the wave propagate through it. Yeah, it can modulate either the intensity, the phase of the wave, a light wave inside it, with, or polarization, or transit time of light. Sensors that vary the intensity of light are the simplest, since only the simple source and detector are required. So how does an optical fiber transmit light? Usually, optical fiber structure consists of these three layers. We have a fiber core, which is surrounded by an envelope material, and the outermost layer, there is a safety layer to hold them all intact. The fiber core and envelope are two different optical material, which has N1 and N2 refractive index respectively. And in order that light can travel inside, usually then the N1, the refractive index of the fiber core should be larger than N2, the refractive index of the envelope. Okay, so this is why, because it needs to be larger, so that then the light will be refracted. The light from N1 towards N2 will be refracted away from the normal light. And when it is away, when that light from N1 towards N2 is above certain angle, critical angle, then it will be reflected back to the fiber core. And this is how it works. So that then it will, through the internal reflection of light at the interface between the fiber core and envelope materials. Through it will travel like this inside the fiber core. In order that the angle is above the critical value, theta c. So here, then the angle here has to be smaller than certain angle. The angle that goes towards the fiber optic has to be smaller than certain angle. Has to be close towards this perpendicular line. Yeah. So that then the refracted light could have an angle larger than certain critical angle. Okay. The angle of incidence, theta I, should be smaller than this. This is the angle of incidence. Then theta C. Yeah. arcsine of n1 square root of n1 square minus n2 square divided by n0. So n0 is equal to 1 at the refractive index of the atmosphere. So the refractive, this equation can be represented as the incident angle should be smaller than theta 0, yeah, equals to arcsine of square root of sine n1 square minus n2 square. So this incident angle has to be smaller than this. Some basic characteristics in optical fiber. When you purchase optical fiber, you will see this in a data sheet. First one is the numerical aperture. And A equals to arcsine of n square root of n1 square minus n2 square. This is the capability, represent the capability of the optical fiber to collect light. The larger the NA, the more powerful the optical fiber is. Okay? Because it means then there are huge difference between N1 and N2. No matter how large the emitting power is, only in the case when the angle of incident is smaller than 2 theta c will the optical fiber be conductive. That light can go through, can be propagated through that optical fiber. When the angle of incident is too large, the light will escape. It will cause leakage of light. And based on the modes of the optical fiber, we have here either multi-mode or single mode. Different transmitting mode when we have a different angle of incident. Some fiber optic in single mode requires that all the incident angle only have a single incident of light, single incident angle. So these are now the application of photoelectric sensors we have mentioned earlier as part used in pulse oximeter, of course, to detect the transmitted radiation or the reflected radiation from the blood vessel, where then we can deduce from there the content of the oxygen level inside the blood. Except this is quite important sensor now in the pandemic time, because many of the patients can undergo hypoxemia, where it has very low oxygen content in the blood. And this oxygen content can be measured using pulse oximeter. So like this, you have infrared red light goes through your tissue, your finger tissue, and on the other part of the finger, you have a photosensitive sensor. Usually, it will then measure the wavelength, this infrared light. You could also measure not only the infrared, you could also measure the red, and then measure the ratio between the two. The fiber optic can also be used as temperature sensor, where incident like this, incident light, and this liquid crystal behavior will be affected by the temperature. So then the curvature also will change, and this will change also then the travel length between this incident point and the reflected point. So the time of light, you can measure the time if it is pulses, that then it is connected to the temperature that creates the liquid crystal curvature here. So this optical fiber then can be used to measure the body temperature inside, not outside, but for really the temperature inside at a specific location. For example, the hyperthermia in specific tissue that is tumor, it becomes tumor. So you could put the optical fiber inside hypodermic needles or inside a catheter, goes through the patient's body to go to where the suspected tumor tissue. Then you inject thermal radiation to it. So usually then the tumor tissue will have different thermal characteristic compared to the normal tissue. Then you can identify which of the tissue are tumor Okay, so that will be all for the photoelectric sensor.